This video is an introduction to trigonometry. In Greek terminology, trigonometry means measurement of angles. And originally, it dealt with relationships among sides and angles of triangles. With the development of calculus and the physical sciences, we now consider the classic trigonometric relationships as functions with the set of real numbers as its domain. Remember that if we're considering an angle, the angle is formed by rotating a ray about its endpoint. So remember that would be the initial ray, the initial side of the angle, and the angle opens that way to the terminal side. That point is referred to as the vertex. So the ray, the initial side, goes to the terminal side and makes that angle. When we refer to angles, we will consider them in standard position. In standard position, the initial side is always on the x-axis, as you see here, and the terminal side is always not on the x-axis, or wherever it ends. So positive angles will open this way, counterclockwise. Whereas negative angles are going to open clockwise, or the other direction. Now when we're looking at these angle measures, we've learned degrees, but degrees is not the only way we can measure angles. Another way that we can measure angles is in radians. So if I consider a circle here, let's just say it has radius r, then this angle theta, how you say it is like that, theta. It's kind of written like a zero with a line, a horizontal line in between. And this angle, theta, is there such that the arc that's subtending the angle is equal to r. Let me kind of draw that. Meaning this arc that subtends angle theta is equal to r. That measure of angle theta is 1 radian. So when we refer to radian, it is the measure such that the arc that subtends that angle is equal to the radius of the circle that you are referring to. That angle measure would be 1 radian. Now, if we consider one full rotation, so all the way around, we know that that is a circumference of 2 pi r. And when we think of this 1 radian, it's like 1 radius that we saw. This would be 2 pi r, or 2 pi radiuses, so to speak. So the measure of angle x is 2 pi radians. So if we think about what we know as a circle going all the way around, we know that that's going to be 360 degrees, which is 2 pi radians, or radiuses, since we're getting 2 pi worth of those from the circumference. So if I want to convert from degrees to radians, I need to use this idea that 2 pi radians is equal to 360 degrees. And we know that from the previous slide. If I go around the whole circle, that would be an angle of 360, and we just saw from the circumference that that is 2 pi radians. If I divide both sides by 2, I get that pi radians is equal to 180 degrees. And I'll use this fact to convert from degrees to radians and radians to degrees. So for example, if I wanted to convert 60 degrees into radians, or if I wanted to convert pi over 4 into degrees, so imagine unit cancellation. I can set up the ratio pi radians over 180 degrees. Then my degrees are canceling, and I'm left with pi over 3 radians. I can take this same idea, the same ratio, pi radians equal to 180 degrees. Those are radians, pi over 4 radians. So if I'm going to multiply that by the ratio 180 degrees over pi radians, my radians will cancel, and I'm left with 45 degrees. So using pi radians equal to 180 degrees allows us to go from degrees to radians and radians to degrees. There are a few common angles that we deal with very frequently. So when we look here, this would be a theta equals 0. That would be theta equal to pi over 2. This would be pi. This would be 3 pi over 2. So if I'm looking at 30 degrees, for example, that would be pi over 6 radians. 45 degrees would be pi over 4 radians. You're going to notice that I've used the abbreviation rad. Many times if you just see rad like that, it means radians, and over time we're actually going to drop the rad altogether, and you're just going to know by looking at pi over 6 that that's in radians. And you can do the conversions on your own to double check those. So these are some other common angles. This is quadrant 1. This is quadrant 2. This one is 3. This one is 4. So remember, our angles in standard position start at the horizontal axis, the x-axis, and opens up counterclockwise, and that's the same way that our quadrants go. In this quadrant, our angles will be between 0 and pi over 2. Pi over 2 is 90 degrees. As you can see, this forms a 90-degree angle down at the bottom. Pi is 180 degrees. You'll notice it's a straight line which has an angle measure of 180 degrees, and so on. In quadrant 2, your angle measures are going to be between pi over 2 and pi. In quadrant 3, they'll be between pi and 3 pi over 2. And then in quadrant 4, they'll be between 3 pi over 2 and 2 pi. Specifically, we can look at something called the unit circle. Prior to this, we've just been looking at a general circle, but a unit circle is specifically a circle that has a radius equal to 1. Recall that the equation of a circle would be that x squared plus y squared equals 1. Since the radius is 1, notice those points there are all on the circle with radius 1. These values you see here that I just pointed to are angle measures. So if you notice, if you are right there at 1, 0, that would correspond to an angle measure of 0. If you're that point next to that pi over 6 that I pointed to, that would be an angle measure that would be pi over 6. So to investigate this a little bit further, we're just going to kind of look in at quadrant 1 only. So if you look at this picture, this is just an excerpt taken from the unit circle from quadrant 1, just to focus there. So if I first consider at 30 degrees, I can make this triangle. And I have a 30, 60, 90 triangle, and I know that my sides will be in this ratio. If I wanted to make this specific to our problem, I can look just at this triangle. I know the radius is 1. So if the radius is 1, I can put that in. And then I can change 30 degrees to radians, because when we're dealing with trig, we're primarily in radians, and when we get into calculus, we're primarily going to be dealing with radians. So I want to write this as pi over 6, and then that would make this pi over 3. So now that I have filled in my angles in radians, I can now use the relationship of the 30, 60, 90 triangle. I know my hypotenuse here is 1, so that would mean short leg would be 1/2. And then that would mean that long leg would be the square root of 3 over 2. So when I consider the angle of pi over 6, that is this angle that I just drew. Starts at the horizontal line, opens up pi over 6. When I consider this, I can consider the sine of pi over 6. So looking at this right triangle, the sine of pi over 6, remember, is opposite over hypotenuse, which gives me 1/2. I can then look at the cosine of this same angle of pi over 6. It's adjacent over hypotenuse, which simplifies to that. Then I could also look at the tangent of pi over 6, which is sine over cosine, or opposite over adjacent. And I could simplify and get this. Oops. So these are all of the 3 main trig functions in the first quadrant for 30 degrees or pi over 6. We can continue this for the other angle measures. So again, we're still in quadrant 1. So now if we consider 45 degrees, I can look at this triangle, and in my 45, 45, 90, I have these relationships. So if I examine just that triangle there, I can convert the 45 degrees into radians, which is pi over 4. So this is pi over 4, and this is pi over 4. I know that my radius is 1. Since I know my radius is 1, I can use the information from 45, 45, 90 triangle to find the legs of this triangle. So that would be 1 over the square root of 2 and 1 over the square root of 2. Sometimes you'll see people write that as the square root of 2 over 2, or I like to say rad 2 over 2. Now, we can consider this angle, that 45 degree angle, which is pi over 4. I can find sine of pi over 4, which is opposite over hypotenuse. I could find the cosine of pi over 4, which is adjacent over hypotenuse. And I could find the tangent of pi over 4, which is opposite over adjacent. I can do this again with the angle measure of 60. So there's my 60 degrees. Here's my right triangle. That would make this 30. Here are my side lengths and relationships for a 30, 60, 90 triangle. I can draw this triangle specific to what we have. So a radius of 1, 60 degrees is going to be pi over 3 radians. So this is pi over 3, that's pi over 6. Then I could use, oops, not what I wanted to do. Getting too excited here. There we go. Then I could use the fact that the hypotenuse is 1, and use the relationships in this 30, 60, 90 triangle so that I can come up with the sides 1/2 and rad 3 over 2. So considering this angle measure of pi over 3, sine of pi over 3 is opposite over hypotenuse. I can find the cosine of pi over 3, which is adjacent over hypotenuse. I could also find the tangent of pi over 3, which is rad 3 over 2 over 1/2. And there we have it. So we can bring all of this together onto one big unit circle. So notice this is the same unit circle we had before. You will notice that the angle measures are in radians. So all of these points that I put in red are points on the circle. So if I just let point x comma y, be the red points I just drew, be on the unit circle. And with angle t. If this is the case, then x will be equal to cosine t and y will be equal to sine t. We use that relationship a lot, that x is cosine of the angle and y is sine of the angle. So consider if I looked at the angle to be pi over 6. Well, cosine of pi over 6, we just saw, was square root of 3 over 2, and sine of pi over 6 was 1/2. So at that angle t of pi over 6, that point right there has coordinates of rad 3 over 2, comma 1/2, because the x coordinate is cosine and the y coordinate is sine, or corresponds to cosine and sine of that angle. We can do this for all of the red points that I put on the unit circle. So here, sorry, hold on one second. I might have jumped ahead. Okay, maybe not. Sorry, so we have some other trig functions that you are familiar with. So we have sine, cosine, tangent, cosecant, secant, and cotangent. You are familiar with sine and cosine and tangent. However, cosecant is something that you're not familiar with. Cosecant is written as CSC of x. Secant is written as SEC x, and cotangent is COT. Just like we know tangent is sine x over cosine x, or opposite over adjacent, cosecant is 1 over sine, secant is 1 over cosine, and cotangent is 1 over tangent, which we can then write as cosine x over sine x. So if you wanted to kind of see these color-coded, there it is. For me, I like to remember that the cosecant pairs with the regular sine, and the secant pairs with the regular cosine. So the cos don't go together. Cosine does not go with cosecant. Cosine goes with secant, cosecant goes with sine. So here is my unit circle, and it looks overwhelming, but again, unit circle, sorry about that, not ready yet. When I look at this unit circle, we saw how to come up with the rad 3 over 2, comma 1/2 that we see at the point for the angle measure of pi over 6. And we can do that for the entire circle. We'd already looked at the first quadrant. What you're going to notice about all of the other quadrants is the measures are the same except for a difference in the sign. So when we look here in the first quadrant, all trig functions are positive. When we look in the second quadrant, in the blue, that's the y coordinates are all positive. That's the signs are positive. When we look here in the third quadrant, we notice that they're both negative, which would mean then that the tangents are positive. And then when we look in the fourth quadrant, we see the first term, or the cosine, are positive. So many times you will see something like this that I wrote on the side, where the A, S, T, C. So all, and then the sine, and then the tangent, and then the cosine. Some people like to remember it like the quadrants, and they think all students take calculus. That's one way to remember it. However, for me, I tend to just think back to the sine being the y coordinate and the cosine being the x coordinate, and it kind of helps me with that. When we're looking at these functions, the trig functions can be even and odd, just like regular functions. So let's just kind of remind ourselves that a function was even if f of negative x was equal to f of x, and odd if f of negative x was equal to negative f of x. Also, recall that the whole idea of the positive angles go up and negative angles go down. So when we are considering f of negative x, we're considering what's happening when the angle measure is negative instead of positive. So remember, all positive, sine, tangent, and cosine. So if I consider cosine of negative x, let's say, I'm trying to examine if cosine is even or odd. Well, that's just going to be cosine of x, because whether I go up or down, cosine is going to be positive in both quadrants. For that reason, regardless if I do a positive angle x or a negative angle x, I'm still getting the same value of cosine, which is that positive value. So we would say that cosine is even. With cosine being even, we're going to find the same thing to be true for secant. And that's because secant is 1 over cosine. So if cosine is even, secant is also going to be even. If we consider sine, well, this is going to be negative sine of x. And let's take a look. If I go up here, then sine is positive. But if I go down the same measure, then my sine is negative. So it's going to have the same value, just a different sign. And so you'll see sine x is the same, but negative out in front. This is true for cosecant. This is also true for tangent. And it is true for cotangent. So cosine and secant are even. Sine, cosecant, tangent, and cotangent are all odd functions. So for the most part, we remember the first quadrant, and then we're able to use the first quadrant to figure everything else out. So if I let theta be some angle that is in standard position, then its reference angle is the acute angle theta prime formed by the terminal side of theta and the horizontal axis. So what I mean, I'm going to have a couple here. So let's pretend I'm only going to look at quadrant 2, 3, and 4, because if it's in quadrant 1, then we don't need a reference angle. Those are the angles that we were dealing with initially. So if I'm in quadrant 2, then my angle looks like that. So when we talk about that angle there in yellow is going to be my reference angle. It's the angle that is formed, the acute angle, the terminal side and the horizontal. If my angle is in the third quadrant, then I look something like that. So my reference angle would be this right here. If I'm in the fourth quadrant and my angle is that, then there is my reference angle. So to think about it, the reference angle is the angle that makes the special right triangle. So there's our special right triangle, there's our special right, and then there's our special right triangle. So we use the reference angle to help us figure out if it's going to be rad 3 over 2, rad 2 over 2, or 1/2. and then we use the fact that sine, cosine, tangent are positive in particular quadrants to help us solve the final question. So let's take a look at some examples. So I want to find the reference angles for these functions here, or excuse me, for these angle measures. So just to kind of get ourselves oriented, if I'm looking at a theta measure of 7 pi over 6, pi would be like 6 pi over 6. So if I need 7 pi's, that means I have to go past the pi, and I end up over here in quadrant 3. So there's my 7 pi over 6. So my reference angle is that yellow piece, which would just be pi over 6. If I'm considering 2 pi over 3, then I know that this is 3 pi over 3. So if I need 2 pi over 3, I'm going to be before that and over here. So my reference angle is that little yellow piece there, which would be pi over 3. And in this last case, again, I've got my 0, I've got my pi. There's my 4 over 4 pi, and this is essentially 2 pi. So if I change that to over 4, that's going to be 8. So if I need 7, that's going to put me over here in the 4th quadrant. My reference angle would then be this, which is pi over 4. So we're going to use these reference angles to help us find sine, cosine, and tangents for angles that are not in the first quadrant. So for example, if I wanted to evaluate each trigonometric function, so we've got a couple here. Oh, sorry about that. Hold on a second. So if I have cosine of 4 pi over 3, I need to kind of figure out where I'm at. There's my 0, there's my pi, that's 3 pi over 3. So if I'm 4 pi over 3, that means that I'm going to be way over here. So cosine is negative in that quadrant. So cosine of 4 pi over 3 is going to be negative of the reference angle. Oh, dang it, sorry. Still getting used to this. Give me a second. There, almost. There we go. So because cosine is negative in that quadrant, that's where the negative is coming for, you see in green. Then we could take the cosine of the reference angle to figure out what the numerical value is, and we still have that negative. So cosine of pi over 3 is 1/2. So our final answer is negative 1/2. Let's look at another one. Let's say I wanted to do sine of 5 pi over 6. So I've got my axes here. If I've got 0 to pi, that's going to be 6 pi over 6. So that means 5 pi over 6 is somewhere over there. In that quadrant, sine is positive. So sine of 5 pi over 6 is still going to be positive of the reference angle, which is pi over 6. Sine of pi over 6 is 1/2. So notice, by using what we know about the sines and reference angles, we can find the value of the trig functions at any angle measure that we'd like. Here's another example. Cosecant of 11 pi over 4. So we're looking at pi over 4. So that's 4 pi over 4. Remember, that's 2 pi, which is like 8 pi over 4. And so keep going, then 12 pi over 4. So 11 pi over 4 is going to be where this arrow ends. So it goes all the way around once and ends up in the second quadrant. So there's my angle measured there. Remember that cosecant of pi over 4 is the same as 1 over sine of 11 pi over 4. So in that quadrant, I know that sine is positive. So I can keep this positive and use my reference angle. So there it is. Sine is positive in the second quadrant. So then that's 1 over square root of 2 over 2, which then is 2 over the square root of 2, and I could simplify that to the square root of 2. Let's see another. I want the tangent of negative 3 pi over 4. So again, have my axes. If I'm over 4, then that's 4 over 4. Negative, so I got to go down, and I'm 3 pi over 4, so I don't pass the 4, end up over here. So tangent in that quadrant is positive. So tangent of negative 3 pi over 4 is going to be equal to positive tangent of the reference angle, which is pi over 4. Tangent of pi over 4 is 1, and there you have it. Sometimes we are able to use some identities to help us solve problems. So there's a ton of identities. Specifically right now, we're going to look at the Pythagorean identities. And essentially the identities are just relationships between the trigonometric functions. So just like in a right triangle, we have the Pythagorean relationship that says if you have a right triangle, then if you square the two legs and add them together, you get the hypotenuse squared. So very similarly, we're going to have some Pythagorean identities. Now, sine squared theta plus cosine squared theta equals 1. That looks just like side squared plus side squared equals hypotenuse squared. If you consider a unit circle, we know that the x value is cosine, the y value is sine, so that kind of follows straight from there. If we divide everything by sine squared, then we can end up with this. Dividing everything by cosine. We can end up with this, and then if we divide everything by sine, we can end up with that. So those three are the Pythagorean identities. So just some notation here. When it's written, like this, that is read as sine squared theta. What that means is that sine of theta is what's being squared. We don't write it like that because we don't want that squared term to get in the way of the sine, meaning we don't want it to get confused with what I wrote second. So when sine is being squared, you're going to see the square right over the n as a superscript. If you see the square not next to the sine, next to the theta, then that means that the angle measure itself is getting squared, not the sine of the angle measure. So let me show you some examples. If we let theta be an acute angle, such that sine theta is 0.6, and we need to find the value of cosine and tangent using the trigonometric identities. So I have the formula that says sine squared theta plus cosine squared theta equals 1. So I'm going to take the value they gave me and plug that in. And now I want to solve this for cosine. Now I've written it just as the positive square root. The reason I've done that is because when we look at an angle measure, theta, it is an acute angle, which means it's going to look like this. It means it's going to be in the first quadrant, and in the first quadrant, cosine is positive. So that's why I only want the positive value of the cosine. So there's my answer. If I want to find the tangent, remember tangent is sine theta over cosine theta. So then I can just divide the values I have, and I would get 0.75. Let's do one more. So again, I'm going to let theta be an acute angle, but this time in quadrant 2, such that I have sine equal to 1/3, and I want to find the cosine and the tangent. So again, I'm going to use my formula, sine squared theta plus cosine squared theta equals 1. I'm going to plug in the values that I have for sine theta, and I get cosine squared equals 8/9. So I take my square root. This time, notice that I took the negative. So let's consider this. Cosine is negative in the second quadrant. For that reason, I get my final answer. They told me that the angle was in the second quadrant, and cosine is negative there. That's why I take the negative. And I've just simplified the fraction and the radical. Then I could find, Then I could find the tangent by using sine theta over cosine theta. And then I'm just going to simplify this a little bit more. So when we look here, because they're both being divided by 3, that's how I'm able to get to that point. Then lots of times we like to rationalize the denominator, so that's why we're going to multiply top and bottom by the square root of 2. In doing so, I get my final answer to be negative square root of 2 over 4. And that's the end of the video.